Hello everyone, I'm Tianle and you can just call me Tyler. This will be my second time being a ULA. Previously I helped with CS16 and this time I'm pretty interested in Professor Matney's CS64. I want to be a ULA because helping others is really a pleasure for me, and by being a ULA for a quarter I enjoy it a bunch. So it will really be my pleasure to be a ULA again in the future. Okay, so the problem we are going to solve today is the translation of this recursive C++ function into a recursive assembly function in MIPS. The function call in MIPS is in all assemblies are pretty complicated because we need to do the stack management ourselves. So I picked a simple C++ program to translate. Okay, so let's get started. First, by looking through the C++ program here, we don't need any constant or static variables. So we're gonna just skip the data part in assembly. We're gonna just start from text. And the first thing we need to do is to put down the functions we need. The first one is, of course, my function, which is the recursive function. And the second one is the main function, which will call the recursive function and print its return value. Okay, the first thing we need to do in the myfunc is actually storing the return address to the memory, because the return address is stored in the RA register, and the RA register will be overwritten if we call another function. And in this case, since it's a recursive function, it will always call itself, and it will just always rewrite the RA register. And to keep everything consistent with the MIPS calling convention, we need to keep RA preserved. So before doing anything, let's just allocate some space on the stack and store our RA register there. To allocate space on stack, we can do it just by moving the stack pointer. And I choose to use the instruction add unsigned immediate value to move our stack pointer by -4. Because remember, the stack in MIPS grows downward, so we need to do -4 here. And then we can use the store word instruction to store our RA register to the stack pointer, offset it by 0. All right. After doing this, we can get started on our program. So here we need to handle the if statement, and by looking closely into that, we can see that if the input parameter is less than or equal to 1, then we return a constant 1. So we can actually preload our return value to be 1. And according to the MIPS calling convention, the return value will be stored in the v0 register. So we just preload the v0 register by 1. And now we need to do the if branch. So if n is less than or equal to 1, we can say we can use the branch on less than or equal to instruction. And our first parameter will be a0. Second parameter will be 1. But 1 is the immediate value, and the BLE is not really happy with immediate value. So since we have already preloaded our v0 to be 1, we can just use the register v0 here. And if that's the case, we are at our base case, and we should return 1. Since 1 is already in our return register, we just need to return. So we're gonna branch to somewhere, just call it return. And in the return label, I'm gonna say that we need to return to the original function, jump to the return address, right? No, not actually, because remember here we already stored our current return address to stack. And accordingly here, we need to retrieve that value from the stack and also deallocate the space used by it. So we're gonna load word RA, offset by 0 on stack pointer. And after retrieving the RA, we need to deallocate the memory space. So we can do it by adding 4 to the stack pointer, because here we minus it by 4. So here we add it by 4. All right, so that should be it. The base case should be completed. So the next step will be handling this, which is the recursive case. And to do the recursive call, we're actually, here it's actually using a shortened command or instruction in C++. And by expanding it, it's actually setting a temporary variable to store the return value, and then add the return value by n, and then return this value. So this will enable us to do a line-to-line translation in MIPS. But one thing to pay attention to is that we are going to use the value of n after a function call, and in the MIPS, n is passed in as in the register A0. And because according to the convention, the A0 register won't be preserved during function call, and here we need to write to A0 with a different value. So we actually need to store the register A0 to a preserved register. And according to the convention, the S registers are preserved. So we can say move A0 to S0, which will store the value of n. But here comes another problem. Since we're writing to the S0 register, we're actually overwriting the value it used to have. And that's against the MIPS convention. So before we write into it, we need to store the value of it somewhere. And yes, we can do it on the stack. So instead of allocating 4 bytes here, I'm gonna allocate 8 bytes. And 4 bytes are used for R8, and the other 4 bytes are used for the S0 register. So here we're gonna store the S0 to stack pointer offsetted by 4. And whenever we change this, we also need to change the recovery or restore of the register. So we'll just change this to load word and deallocate by 8. All right. So we have already handled the memory and A0, like the value of n. Now it's time to really do the function call. We need to prepare the argument for the function call, which is n-1. And since we have our n in A0, and the A0 will also be used as a parameter for our next function call, so we can actually decrement the A0 register by 1. So here I'm gonna add an immediate value to A0 by -1. Okay, so here we have our argument prepared, and then we can just do the jump and link to call the function. Call ourselves again, and we can expect a return value from this function to be in V0. All right, so we have already finished this step, and the temp here will be our register V0. The next step, we are going to add the V0 by n. So we are going to say that add V0 to be V0 plus the original n. Since the n here is decremented by 1, we need to put the value of the original n, which is the value we preserved in S0. Okay, and after that, we can just return our function. We can just jump to return. But hey, return is right here. So this is an extra step, because the assembly program will run all the way through. So it will just run into the return area automatically. Nice. Okay, so that's our recursive function. We have handled both the base case, which is return a constant 1, and our recursive case, which is doing the recursive function call and manipulate the return value. All right, the next step will be this. First, we need to call the function with 5 in the main function. So we load our first argument, which is n, to be immediate value 5, and then we jump and link my function to call the function. And the next step will be printing out the value. Okay, so we do a move because the return value will be stored in v0, and the system call of printing an integer will pull the value from a0. So so we should do move v0 to a0, and then we need to print an int, so we load the v0 with the service code of 1, and then we do the system call. All right, that's the end of the program. So we need to do the return 0, although I didn't do it in the C++ program, but I should definitely add a return 0 here. I'm sorry. It's not the best practice. And in the MIPS, we also need to return 0, which is just simply loading v0 with 10 and do a syscall. That will indicate the end of the program. All right, let's try to run it. Let's do spam-f for file, and then recursion.asm. Got a nice little 15 right here. Okay, that's the value produced by our assembly program. Now let's try to run the thing in C++ version. I will just call it C++. Oh, oops. I didn't add semicolon for this. Okay, let's try to run the CPP, and you can see identical result. All right, we have successfully translated this recursive C++ function into MIPS assembly. Thank you for watching. Bye.